Okay. Hello, everyone. Welcome to week 4, I believe, to another video. Today, we're going to be talking about the introduction to transformers. Now, last week, we talked about neural networks and backpropagation. We're going to be focusing on the transformers of the world. So, these are more akin to the likes of ChatGPT, how they work, how these generative AI work. And we're going to be looking into a deep dive as to what are transformers um, and why they're so important. Now, important note, it was actually Google. They had a research paper come out about transformers, I believe somewhere in the year of 2017 or 2018, and it kind of like changed the landscape of how AI could actually function with the use of LLMs and generative AI. So, first we need to understand what transformers are. So, transformers. No, not the robots that you see in movies directed by Michael Bay. Rather, transformers are a type of neural network and a machine learning model that underlines the current boom in AI. Stuff like ChatGPT, which, by the way, GPT stands for Generative Pre-trained Transformer, is a type of model that's powered by transformers. Generative means it generates new text. Pre-trained means the model learns from a massive amount of data and it can be fine-tuned on specific tasks. And finally, the transformer is a special kind of neural network. Large language models, like LLMs like ChatGPT, predict the next word in a sentence. That's their entire foundation. They take the original question and the next predicted word as an input, then predict the next word, and so on until a complete answer is produced. Transformer-based models can perform various tasks, including generating text, producing synthetic speech from text, creating images from text descriptions, such as DALL-E or Midjourney, as you might have heard, and translating languages. When interacting with chatbots, the models repeatedly predict and sample the next chunk of text to generate a story based on seed text. The models predict the next word by taking a random sample from the distribution it just generated, appending that sample to the text, and then running the whole process again to make a new prediction based on all the new text, including what it just added. That way, it has context of what to generate the next word or token. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant. This is also known as a system prompt. And then using the user's initial question or prompt as the first bit of dialogue, and finally having it start predicting what such a helpful AI assistant would say in response. The computation at Transformer looks like matrix vector multiplication. Sorry, I'm a little bit sick still. And it is important to distinguish between the weights of the model, the brains learned during training, and the data being processed, the specific input fed into the model. So let's talk about the high-level data flow in a transformer. First, we have to talk about the process of tokenization. Any input is broken into tokens when given to a large language model or transformer. Um, so these tokens, which are words, parts of words, or character combinations, and they are turned into tokens, which are basically numbers. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. The model has a predefined vocabulary, which is a list of all possible words. There's also embeddings. So each token is associated with a vector that encodes its meaning. Words with similar meanings have vectors close to each other in a high-dimensional space. For example, in GPT-3, the vectors have 12,288 dimensions. The first matrix encountered, the embedding matrix, has a single column for each one of these words. These columns determine what vector each word turns into in that first step. We also have something called an attention block, where vectors talk to each other, passing information to update their values. The attention block figures out which words are relevant to update the meanings of other words. There's also a multi-layer perception MLP block. Vectors are updated based on the answers to questions asked about each vector. Then there's repetition, where this process essentially repeats, alternating between attention blocks and MLP blocks. And then the last vector, the probability distribution, is basically to produce a probability distribution over all possible next tokens. A snippet of seed text can be fed into the model, and it repeatedly predicts what comes next, sampling from the distribution, appending it, and repeating. So this is that attention block here, and this is our MLP. Now, in deep learning, deep learning models use data to determine how a model behaves rather than explicitly defining a procedure. A flexible structure with tunable parameters is set up. An example of that desired output for a given input are used to adjust the parameters. Deep learning models scale well and use the backpropagation training algorithm. The input must be formatted as an array of real numbers, often called a tensor. The input data is transformed into distinct layers, each structured as an array of real numbers, until the final layer is reached, which is the output. Model parameters are referred to as weights, and they interact with the data through weighted sums. The 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices, which fall into 8 different categories. Now, word embeddings numerically represent words in such a way that they capture the meaning of the word. A vector, which is a list of numbers, can represent a word by answering questions about it. For example, does this person have authority? Real-life models use high-dimensional embeddings, for example, 3,000 dimensions in Google's Word2Vec and 12,000 dimensions in GPT. In the embedding space, vector arithmetic can produce meaningful results. Example given, if you took a king and a man and you added a queen, if you subtracted a king from a man and added a woman, you would get a queen. During training, the model finds it advantageous to choose embeddings such that one direction in the space encodes gender information. The dot product of two vectors measures how well they align. It is possible when vectors point in similar directions, 0 if they're perpendicular, and negative when they point in opposite. The embedding matrix consists of columns that tell us what happens to each word. In GPT-3, the vocabulary size is 50,257, and the embedding dimension is 12,288, which results in about 617 million weights. Now, contextual embeddings, there's a problem with static embeddings. It's a problem that they cannot represent two different meanings of a word based on the context of the sentence. So, for example, here we have a rice dish, and then we have an Indian rice dish. So you need to be able to tell the differences between these, or even words that are used in different contexts. Now, contextual embeddings are needed to capture the meaning of a word based on the surrounding words. To generate contextual embeddings, the original static embedding for a word is influenced or changed by all the other words so that it can capture the meaning of all these adjectives. The prediction of a word is influenced not by just a few words which are prior to that word, but it can be influenced by some words which are far out in that paragraph. Now, the transformer architecture, which includes an encoder and decoder. Yes, the encoder takes the input sentence and generates a contextual embedding for each word or token, and the decoder takes the contextual embedding from the encoder and predicts the next word. Now, we're going to look at two things, BERT and GPT. That you should note that BERT has only the encoder part, while GPT only has the decoder part. Now, let's quickly talk about encoders. So, encoders essentially take an input of a sentence and tokenize it, and special tokens are also added, stuff like CLS and SCP. Each token is assigned an index from the vocabulary. Then each token ID is converted into a static embedding vector using the static embedding matrix. A position embedding vector is added to each static embedding to incorporate word order information. The transformer processes the entire input or sequence in parallel and needs knowledge of that order. Words need attention from surrounding words to produce a contextual embedding. So these concepts are used to compute attention scores, a query, key, and value. For example, the query is like a question. Like, I want to know about my modifiers. The key is a description that each word gives about itself. Like, I'm an adjective describing taste. And the value is the component that each word contributes to the query. Attention scores are computed based on the dot product between the query and key vectors. Static embedding is added to all these vectors, and all these vectors can be thought about as riceness, Indianness, and so on, just like we saw over here. To build these vectors, the positional static embedding for each of the words and tokens is taken and multiplied by a special matrix called WQ. WQ knows how to encode the query of a token for attention computing. A similar process is done with magical matrix WK. WK knows how to encode key of a token for the attention computation. WV knows how to encode value of a token for attention computation. There's also something called a softmax function, which converts the attention scores into a probability distribution. The attention scores are then used to weight the value vectors, and the weighted values are summed to produce the contextual embedding. Now, there's also something called multi-head attention. This was also about the contextual embedding, and you can see that here. Oops, I went too far. So let's go back really quick. Here. So multi-headed attention. Multi-attention heads allow the model to focus on different aspects or relationships between tokens. One attention head might focus on adjectives, another on verbs, another on pronouns. It's basically looking at different aspects of different relationships between the tokens to enrich the contextual understanding of each token. After the attention heads, the embeddings go through a feed-forward network. The feed-forward network enriches each token embedding by applying non-linear transformation, enabling the model to learn complex patterns and higher-order features. The weights and parameters are set during the training process. The result embedding that you get is even more enriched, and the enriched embedding is added into the original embedding, resulting in the final contextually rich embedding. Now, let's take a quick summary of the encoder. So the input sequence is taken, a static embedding is generated, then a positional embedding. A transformer block or NX layer is used, where the model normalizes, uses VKV to compute the attention score or attention weight, has multiple such heads, and then goes through normalization. The feed-forward network is used when you add the original embedding to the output and get the final contextual embedding and normalize it. At this point, you're getting a final contextual very rich embedding. Then the decoder. The output of the encoder is given to the input of the decoder. The decoder produces the next word, if working on next word prediction, or starts with a special token, produces the translated sentence, if working on language translation. Now there's cross-attention, where the query vector is based on the translated sentence, whereas the key and value vectors are based on the original sentence. Multi-headed cross-attention, where we have the V and K values are coming from the encoder, whereas the Q is coming from the decoder itself. In the case of BERT, which we mentioned earlier, there's only an encoder part, there's no decoder. In the case of GPT, the transformer architecture is different because there's only a decoder. Now there are some additional things to note. Number one, we can add something called a temperature constant to the softmax function, which basically controls the randomness of an output. A higher temperature gives more weight to the lower values, meaning the distribution is a little bit more uniform. And if the T or temperature is smaller, then the bigger values will dominate more aggressively. The inputs to the softmax function are often referred to as logits. There's a difference between inference and training, where inference is when the model is used to make predictions of new data, where training is when the model learns from a large data set. And finally, normalization. Normalizing is very simple. It's like normalizing it to a value, which is 0 mean and 1 standard deviation. Then looking at the VKQ kind of metrics to use multi-headed attention to derive EC1, EC2, and individual contextual embeddings, adding all of them up to produce your final context of an embedding. This is basically how BERT works. So, let's say if you have a BERT-based model, you have 12 such layers. That is all for this week. Thank you very much for watching. We will see you next week. Thank you.